Okay, so welcome to the last session of today, the last session before the conference dinner. Just a reminder, in the program we had a talk scheduled by Srinarayan Ashokkumar on cracking and analysis of the mobile application source code. Unfortunately, the speaker could not make it, right? So therefore we had Ben Stock, who was willing to jump in. And he has also a very interesting talk on the extended same origin policy, and he wants to eradicate DNS rebinding. So Ben Stock, go for it.
Thank you. Okay, so this is on great. So hi, my name is Ben. Because I actually did this talk twice before, but only in a 25 minutes slot instead of a 40-minute slot. I actually added some new slides. So I'm a first-year PhD student at the University of Erlangen-Nuremberg. I did my master's thesis with SAP Research in Karlsruhe, and I want to use this opportunity to thank Martin Jons that he actually made me aware of this conference and also invited me to be here. I also did during my thesis, we actually developed this extended same origin policy, which I'm going to present to you right now. And I'm currently working basically on DOM-based cross-site scripting. We have a paper for CCS on the topic, but just as a spoiler, we found on 9.6% of the Alexa top 5,000 websites some form of XSS vulnerability that we could actually abuse. And since I'm a PhD student, I'm quite poor, so I'm willing to do quite something for free drinks, and I was actually challenged by two of my friends on Twitter to say the words cyber war and banane, and I hereby did this, and I think I earned like three drinks or so. Okay, so now back to the serious stuff. For the agenda, I'm going to first talk a little bit about the technical background necessary to fully grasp our extended same origin policy. We'll then talk about DNS rebinding, so the attack we try to eradicate with our new technique. We'll then give an outline of how history repeated itself in terms of DNS rebinding. So there were quite some attacks that happened, or quite similar attacks that actually happened over a total of 17 years. I will then go into detail on an attack we found, so using the HTML5 offline application cache, and we'll then go actually into details on how to extend the same origin policy, first analyzing what the semantics of the same origin policy are and how they match or do not match the implementations. I will then end with a short conclusion and some insights on future work we're planning to do with this. Okay, so technical background. So just a very brief introduction. Web application 101. Obviously, this is quite clear to all of you. We have a server, we have a browser, so a client, and those two interact with each other. So basically, the client sends an HTTP request to the browser, to the server, maybe containing cookies to authenticate himself, and the server will then respond with HTML content that is rendered in the browser. And this HTML content may actually also contain active content, such as JavaScript, Flash, Silverlight, or such. And active content actually enables the web application to interact with the document that is presented in the browser, so using the DOM API, and also to interact with the server, not necessarily the same server it retrieved the content from. So think of iframes for advertisements and such. And both of this is actually done in the name of the user. So this is obviously security sensitive because we see it down here. We have the cookie that is actually sent, might actually be sent to the server. And also, as I just said, usually have advertisements, for example, that use iframes. And in this case, very obviously, the advertisement will stem from an advertising network and not from the same server our resources were located on. So to have kind of an isolation boundary between these two interacting parts, the access is governed by the same origin policy. So what is the same origin policy? It's interesting color on the beamer. The same origin policy restricts access of active content to objects that share the same origin. And the origin in this case is the notation of the protocol, the domain, and the port that was actually used to retrieve the object. So how does this look? Quite obvious example. We have this example here, http://example.org, port 80. So only the first part is the protocol, so that's HTTP. Example.org is the domain, and port is 80. which could also be omitted since it's the default port for HTTP. And down here we just have a small table that just to get your head around it. If we have this resource or this website wants to access a resource that is located on example.org, HTTP example.org, that works perfectly because they obviously share the same origin. However, if it tries to access a resource at HTTPS example.org, we have a mismatch in the protocol. So access is then denied to that resource. Same holds true for port 8080, which is obviously a mismatch in the port. And the most obvious example is Facebook.com, so I can't just open my website with kitten pictures and read all your Facebook posts and or your friends' Facebook posts, obviously. So the same origin policy is basically also used to protect intranet resources. Let's assume we have this scenario. We have an attacker that's sitting out here on the internet, say at the IP address 6666, and he wants to access a resource that is located down here at 10.0.0.20, for example, some wiki in your company. And obviously, there is a firewall between the internet and the intranet, so the attacker can actually directly access the resource he wants to retrieve, but he actually is able to lure a victim, so somebody who uses a computer inside the intranet, to browse to his site. And what he then does is he embeds active content in his website that then tries to access the resource at 10.0.0.20. So just do a HTTP GET and try to read the reply and then leak it to the attacker. Obviously, as I just discussed in the last slide, the same origin policy kicks in here and prevents access because attacker.org is not the same domain name as 10.0.0.20. So quite obviously, we have a same origin policy mismatch, and the access to the resource is denied. So the attacker can't abuse this. So DNS rebinding is actually a technique that tries to circumvent the same origin policy. So let's see the exact scenario again. We again have the attacker sitting on the internet. He wants to access a resource at 10.0.0.20. But alongside the server, the web server containing this malicious content, he is also in control of the DNS server for attacker.org. So again, when he now lures his victim to attacker.org, what actually happens, and what I omitted in the last slide, first of all, we do a DNS, so the browser does a DNS query. It asks the DNS server, hey, please give me the IP address of the machine that is actually running attacker.org. So in this case, the DNS server will then in the first step reply with 6.6.6.6. But in this packet, the time to live will be set to 1 or 0, so to a very low value. The time to live in a DNS packet is actually the amount of time that the client should cache the response. Sorry. So basically, this means that if after more than 1 second we want to try it and access attacker.org again, we actually have to reiterate the DNS query. Okay, so what happens now is that we retrieve the IP address 6.6.6.6. We now connect to the attacker's web server, render active content again. However, this time the active content does not try to access 10.0.0.20, but actually opens a new connection to attacker.org. However, 1 second in this example might have passed by this, so you can just do set timeout or such. Thus, the DNS query or the DNS reply is actually expired. So the browser must now actually reiterate the query to the DNS server. So in the next step, what this malicious DNS server does, he replies no longer with 6.6.6.6, but he replies with the IP address of the internal server the attacker wants to access. So actually what happens now is attacker.org now resolves to 10.0.0.20. The client can connect to attacker.org, which is now located on the wiki server, for example, down here. And obviously the same origin policy matches, because attacker.org is just rebound to this new IP address. And that's actually why it's called DNS rebinding. So I already said that history has repeated itself in conjunction with the same origin, with the DNS rebinding, sorry. So in 1996, clever students at Princeton actually found an even easier way. What they did is actually for a DNS, you can reply with multiple IP addresses. This is usually done, if for example, you try to look up google.com, you will actually, I think, get 5 IP addresses. This is normally used for load balancing. But in this case, what they actually did is they replied with 2 IP addresses. The first one being the server we wanted the applet to be loaded from, so in our example, 6.6.6.6. And the second IP address that was replied with was actually 10.0.0.20. So the applet then could be downloaded, but would take the second IP address to connect to the server. And again, we had a way around the same origin policy. As a countermeasure back then, actually strict IP-based access control for Java applets was introduced. So Java applets nowadays are only allowed to connect to exactly that server they've retrieved from, so to that IP address. So it's actually stored with the applet during the lifetime of the applet, even in the cache or such. So this effectively stopped exactly this kind of attack. Then in 2002, there were actually two attacks. Quick-swap DNS is basically what I explained when I was talking about the general construct of DNS rebinding. And what also some clever researchers found was they could abuse domain relaxation to conduct DNS rebinding attacks. The domain relaxation is actually a means. If you have two different applications running on two different sub-level domains or subdomains, maybe they want to interact with each other. So what they actually can do is they can relax their origin or their domain. So this actually means they can say, okay, I now want to be in the context basically of my father, of my parent domain. So basically what the attack was about, we have a domain that is called evil.attacker.org, which is actually pointing to our web server on the outside on the internet, and we have attacker.org that is actually mapped to 10.0.0.20, so the IP address we want to retrieve content from. Then inside the script, we can just say, okay, document the domain equals attacker.org, therefore or thereby relaxing the domain to its parent domain, and then accessing the resource at 10.0.0.20. So as a countermeasure, nowadays browsers implement explicit domain relaxation, meaning that if you have two resources and they want to interact with each other, they both need to explicitly set the document domain property. So even the father domain has to actually say, okay, I am really attacker.org. And basically your corporate wiki will most likely not do this. And the second countermeasure was introduced was DNS pinning. What browsers nowadays do is actually they cache, they ignore the time to live value of the DNS reply and cache the IP address that was first retrieved. So therefore, we can't do this rebinding step anymore because the second query that was iterated or that was given to the DNS server is actually no longer taking place. So we can't force the victim to then rebind the domain to 10.0.0.20. And the browser actually, depending on the implementation, so in some browsers there's actually a timeout, a very long timeout of like an hour or such, and in other browsers they just store it until the browser is closed. Then in 2006, my colleague Martin Jons actually discovered, together with another researcher, another nice way to get around the same origin policy or to re-enable DNS rebinding. Firefox and Internet Explorer at that time, when they tried to access a server, and that server would not be reachable, so basically the port was closed or such, they would drop the DNS cache and then reiterate the query. This was actually done to be able to do failover, so if the server was no longer there, then just try to resolve the domain again to get the new IP address of the server. But actually, quite obviously, you can abuse this by just answering the first reply, and then on the second, or answering the first query, sorry, and on the second request from the browser, you just drop the connection, and then it will reiterate the DNS query. Actually, this was also used, or actually led also to many vulnerabilities in conjunction with several active content plugins. So JavaScript, Flash, Java, so basically every plugin there was. And this even allowed socket communication. So another countermeasure, so we had another attack and we put another band-aid on it. In HTTP 1.1, the client must always send the host header. So the host header is actually a commodity feature that is used so you can have multiple domains on just one IP address, and the server still knows, okay, which content should I deliver to the client right now. And host header checking just means, okay, the application must then check whether the host header is actually matching the domain that this application runs on. And as another countermeasure for the plugins, they actually got very restrictive when it came to network capabilities. So for example, Silverlight by default can connect to like, I think 10 ports, 4,500 something. So this is not feasible to use Silverlight in DNS rebinding attacks or in socket communication attacks. Okay, so now we're in 2013, and actually we discovered a new technique that we could use to again and re-enable DNS rebinding. And so the basic idea is to abuse the cache. So every browser has obviously a cache, and our instinct is that if we are able to cache a resource within the browser's cache, so long that the IP, the domain to IP mapping is dropped, then we can actually re-enable DNS rebinding, because then if, for example, a certain piece of flash is still in the cache, this certain piece of flash can then connect to attacker.org, get the new IP address for attacker.org, and do DNS rebinding again. However, we have a problem, because normal caching behavior in the browser can actually not be influenced by us. This comes from the fact that this cache is set by, or is restricted in size by user settings, and also if you do normal browsing on your computer, you actually have a lot of pictures and such that are actually stored in the cache. So this is not something that is reliable, so we can actually say, okay, if the victim comes back to us after 1 day, our content will still be there. However, the HTML5 cache, app cache, sorry, actually enables for a web developer a controllable caching behavior. And for us as an attacker in this scenario, it allows us to store resources so long until we can actually be sure that the DNS pinning times or timeout has expired or the browser has been closed before. Okay, so how does the app cache actually work? As I said, okay, already a developer can actually say, okay, I want to store certain resources in the browser or in the application cache. This is mainly used for bandwidth reduction and also to allow offline applications. So basically, you can just have an application, for example, on your mobile phone that is completely in the offline cache, and you don't need to be online to use this application. So in HTML5, there was a new attribute added to the HTML node in the HTML documents called manifest. And the manifest actually contains a link to a manifest file, and this manifest file then states which resources should be put into the application cache. And it looks something like this. So this cache manifest file tells the browser, please cache for me example.org index.php and example.org //svf. The whole process works as such. We have a browser and our web server. The browser connects to the web server, retrieves the HTML, where it finds the manifest attribute and the manifest file. It then downloads the manifest file, and in turn, after analyzing the file and looking at which resources to cache, it stores them in the application cache in the browser. So if we again go to the same website, and we assume that actually the index file was also cached, then the first request will not actually go to the server, but will go to the cache, the offline application cache. From there, we retrieve all the content, run or execute the whole page, so render the page, run JavaScript as such, and only after we're done with that, we actually retrieve the manifest again to see whether it has changed or not. So this is actually done so you can have the benefits of caching. So it would not make that much sense if you have caching and then have to do a request first to see have any resources changed. But you actually run it once and then check afterwards to decide whether the resources that are currently in the cache should be dropped or should be updated or such. Okay, so how can we use this in terms of DNS rebinding? We are able to persistently store certain resources in the app cache. So say, okay, we want to store resources from attacker.org, so maybe even the index file and flash or such, in the application cache. We then let the victim wait until the victim closes the browser and lure the victim again to our website. On the second try, we actually hand out for the DNS query, so we hand out the internal server IP address. However, since the resources are cached, the website is rendered just as it was before. And so we can actually do, again, DNS rebinding, because now we are in complete control of attacker.org, so we can map it basically to any internet host we want to attack. And then we can obviously retrieve sensitive data and leak it back to the attacker. However, there's a catch in that. So I said on the previous slide that in the last step of this caching process or retrieving from cache process, the browser actually tries to get the manifest file again. So in the fifth step, the manifest file is again downloaded, and remember it is hosted at attacker.org. However, attacker.org is now no longer hosted on the 6.6.6.6 web server, but it's pointing to the internet host. So quite obviously, the manifest file will not be there on the internet host. So in this case, the browser then drops all the data that is stored in the application cache, and we only have one shot to actually retrieve content from any given server. However, if, for example, we have a corporate wiki, it might take some time to actually go through all the pages and retrieve all the interesting content. So nicely enough, there is actually a pretty neat solution to that. We can actually use cross-domain caching. So say we have two domains. We have attacker1.org and we have attacker2.org. Attacker1.org is only responsible for hosting our index file and the manifest file. And in attacker2.org, attacker1.org, sorry, we actually embed, for example, a flash from attacker2.org. The problem with flash, which is very, very important to our attack actually, normally, for example, if you have a script that you include from a different host, then all the script's content will actually run in your context, so in your origin of your website. However, for Flash applets, they don't adopt, so to say, the origin of the page they are embedded into, but they still have the same origin they actually were retrieved from. So what this means is that Flash SVF, although it is actually running on the website attacker1.org, is running in the context of attacker2.org. So what we can now do is, on attacker1.org, we say, okay, please cache for us this SVF file here. We then wait for the victim to close the browser, lure the victim again to attacker1.org, which still has this object embedded, so the Flash object embedded. Still, this contains has the origin of attacker2.org, but again, we rebind attacker2.org, and this way, actually, we are able to, again, do DNS rebinding. And the most important thing here, in the final step, the manifest file is actually downloaded from attacker1.org, which is still mapped to our attacker's IP address. So this actually allows us to do it persistently, so we can actually abuse this. If we're able to lure the victim to our site over and over again, we can actually enumerate hosts in the network by just rebinding attacker2.org every time to another IP address. So this is actually a pretty neat attack. So just as a small example, we also have this in our paper we presented at Usenix last week. As a small attack scenario, so at Usenix I actually got the question, so is a wiki is it really a target? Because in our wiki we need some form of authentication. It might still be a problem. For example, SAP uses authentication based on certificates, and as far as I know, you only have to click on yes, I want to send this certificate once. So once you're authenticated, actually, if the browser is still running, it can access all the content that is actually privileged, and you need to be authenticated to retrieve it. In our paper, we actually discuss CUPS. So I guess most of you know CUPS. It's a well-known Unix printing system, and it actually employs host header checking in its application. So you can actually change anything over the CUPS interface using DNS rebinding. However, as I said, applications must actually perform the host header checking. And there are actually two files that CUPS lets you access over its web server, and that is the error log, and that's the access log, the print log, sorry. So this actually, if I was an attacker and wanted to find out what is going on at SAP right now, I could just use this to actually read all the CUPS logs, retrieve IP addresses of printers, email addresses of printer administrators, and also the names of the files that were printed. So this often might actually be a good indicator on what's going on inside the company right now. So this is obviously a problem, and this cannot be fixed using the host header check, because it's actually just a text file that we can leak here. Okay, so we're back to history repeating again. So in 2013, we discovered the offline application attack. It works pretty well on all desktop browsers except for Internet Explorer. We still have this one-shot chance on Internet Explorer, but Internet Explorer actually doesn't allow cross-domain caching, so we can't use our advanced attack scenario. Also, it works quite nicely on mobile browsers, but again, not for cross-domain, but nevertheless, we can even exploit mobile browsers. And actually, just 1 week ago at WOOT in Washington, Dai and Resik presented their paper called Fire Drill. They actually make use of the fact that the DNS cache is not endless, so they just resolve a lot of bogus domains, and therefore evicting the pinned entry from the DNS cache and thereby re-enabling DNS rebinding again. However, so actually our work was done like half a year ago or such. I just read this on the plane to Washington and was very happy to see that our approach actually fixes this, even though we didn't actually know about the attack before. And that's what's up next. So I want to talk to you about the extended same origin policy. So the same origin policy's duty is to isolate unrelated web applications from each other based on the origins of the interacting resources. I guess you all got that, at least from my introduction. And the semantics of the same origin policy are actually built around two entities. So we have a web client or a browser that's actually whose duty is it to enforce the policy, and we have a web server that provides the resources that are actually subject to the policy. So in a perfect world, those two entities would also be the ones that were involved in the security decision. However, they are actually not, as we see in the case of DNS rebinding, because the entity providing information for the decision that is actually done inside the web client or the browser is the DNS server, because it provides the link between a domain name and an IP address. And as we have seen, the DNS server may not actually be trusted. So the domain name server might actually be under the control of the victim. So quite obviously, we have a principal mismatch here in the semantics versus the implementation of the same origin policy. And our idea is actually to fix this mismatch in the implementation of the same origin policy. For that, we had 4 design goals in mind. Design goal 1 is we want to have client-side enforcement. So the same origin policy, quite obviously, is a client-side policy. So we want to make sure that the security decision is actually done inside the client and not on the web server or by the DNS server or such. Design goal 2 is we want to make sure that it's actually done on the protocol layer, because it's a protocol layer problem. By using DNS, actually. So we don't want to have applications that need to be changed to enable host-header checking. And as we saw in the example of CAPS, sometimes interesting data is not even located inside an application as such, but it might be a log file or a text file or such. We want to have this as a dedicated security functionality. So the host header is actually a commodity feature to run multiple domains on one IP address. It's not actually was not designed to do security. And you never know what's going to happen in 10 years. So maybe in 10 years, the host header will have some other meaning, and then actually this might actually break something. And our design goal 4 for a new policy is actually we want to be non-disruptive. So if we have a web server or a web client that does not implement our approach, we don't want to break existing web applications. That would be really bad. Thus, or in our analysis, we also showed that only the web server should actually be capable of setting its own trust boundaries. So the web server should say, okay, these resources are okay, they may access my content, but now what's actually happening is the client tries to guess this boundary using the triple protocol, port, and domain that are used in the same origin policy's decision-making process. And actually, yeah, that's based on information that was actually delivered by the network or the DNS server, so it's not necessarily the web server that is actually involved. And thus, we aim to fix this mismatch in the implementation and the semantics of the same origin policy. So we propose to extend the same origin policy with some form of server-provided input that is actually delivered through an HTTP header, but not the host header, or well, host header is a request header anyways, but not through an existing header, but through a new one. So we propose that we actually extend this triple of the protocol, port, and domain with a so-called server origin. And this should be delivered by the server in its response as a header. Okay, so how does the same origin policy's decision logic look like? So we have an accessing resource, which is denoted by A, and we have a target resource that is denoted by T over here. So the first line basically is the old same origin policy, so we still want to make sure that protocol, domain, and port match. However, we ascertain that also the second criterion must be fulfilled. So the domain name of the accessing resource must actually be contained in the server origin of the target resource. And if the server origin is not sent by the server, for example, because it doesn't implement our same origin policy, then the second criterion evaluates to true. If you look at this, this is quite obvious that if this header is not sent or not set, then actually we fall back to the old same origin policy decision and don't break anything. So as a small example, say 10.0.0.20 tells that its origin is actually 10.0.0.20 and wiki.corp. And so the second part of the same origin policy decision looks at, is attacker.org actually contained in 10.0.0.20 or wiki.corp? Quite obviously it's not, so the access to the resource is actually denied, and our resources or our internet resources are protected. Okay, so summarizing the extended same origin policy, obviously we are able to do this on the client side, so we meet design goal 1. We use an HTTP header, so we don't necessarily have to touch any running applications, but we can do this in the server module or such. The HTTP header is only used for security, so we have no side effects from header specifications maybe changing at some point, and browsers can actually fall back to the old same origin policy when the header is not sent, and therefore being adhering to design goal 4, not breaking anything. We implemented, to prove the validity of our approach, a very small prototype into Chromium. It's basically only consistent of header extraction, which is done anyway. So the headers are parsed anyway, and they are put into an array inside the browser. And then in that array, we just need to do string matching, so to see whether our origin is actually contained or not. So the overhead is close to 0. I mean, it's just string matching. I guess the network latency is way, way higher. Okay, so how does this actually look? This is the implementation logic for XML HTTP requests. So the first decision, so most of this is actually from the original code and not our contribution. So we have first the decision, is this the same domain request or not? So I'm going to get into that part at the end of my talk very, very quickly. If it's the same domain request, so attacker.org tries to access attacker.org, we now add this check here. So we say, okay, this X server origin header must be checked, and only if this same origin header, this server origin header is set and our criterion is met, so the accessing domain is actually contained in this list, we allow access to the response, to the accessing JavaScript application, for example. Okay, as a conclusion, the same origin policy is the most basic security policy that exists in the browser. Its duty is to isolate unrelated web applications from each other, nowadays based on information on the origin of interacting resources, so basically protocol domain and port, as I've shown before. DNS rebinding effectively circumvents the same origin policy by actually binding 2 different IP addresses to the same domain. And actually, vulnerabilities have been discovered in 1996, 2002, 2006, and 2013. So here we are, 17 years later. We see that DNS rebinding is actually a protocol-level flaw because there is a mismatch, as I discussed already, in the semantics and the implementation of the same origin policy. And thus, we decided to enhance the same origin policy with explicit server origin, so something that was explicitly sent by the web server to set its trust boundaries. And we could actually implement our approach in Chromium, and it proved to have no overhead. Another question I got at Usenix was, okay, but this is opt-in. So you say, okay, you have design goal 4, so you don't want to break anything. However, this is opt-in on the target side. So if you're a corporation and you don't want your data to be stolen, you'll just go this small step and just implement our approach. Okay, so going to future work. Actually, we're now discussing of rethinking the notion of an origin in the browser. So actually thinking about, okay, shouldn't we replace the same origin policy as it is right now? This could actually enable an application. Say we have an application that runs at example.org, and it runs again, or another similar application runs at example.com. So why shouldn't those 2 domains say, okay, we are actually the same application? So by setting the server origin and saying, okay, I am okay with being used as example.org and example.com, we could actually widen the trust boundaries. And the server would then say, okay, this is exactly my trust boundary, and it's not the client that has to guess this anymore. We could also apply the newly developed same origin policy to other parts of the browser itself. So for example, password managers, they store credentials. So if I'm able to send just a site that says, for example, so if I rebind facebook.com, and Facebook employs no host header checking, the victim just enters his credentials. And if I then later on use the same domain and now let it point to my server, then the password manager will actually have stored the credentials for facebook.com, so where the user actually logged in, under my domain attacker.org, which is easily extractable using cross-site scripting, or in this case, just my JavaScript. Also, postmessage is a candidate. In postmessage, the sending resource is actually only identified by the URL. So this is also a problem in terms of DNS rebinding. And what's also very important is to adopt the new policy for plugins. So actually Flash is really bad, as I said before, because Flash doesn't even implement the complete same origin policy. They don't even use the port. So if I have a Flash applet, I can actually use this to connect to any port on the server, on the target machine. So this is obviously quite a big issue, and this should be implemented into plugins as well. And then we also have to rethink the CORS-like pre-flight requests. So CORS is cross-origin resource sharing, actually allowing an application to access a resource that is located on another server. This server then sets the appropriate CORS headers and says, okay, it's okay for you to access this resource. So I'm going to get back to this now really quickly. So now we take a look at the right part. We look at, okay, we don't have the same domain request. And then we look, okay, is this a complex request or is it a simple request? A complex request is a request that actually sets some headers. This is basically used. So if you have CORS and if you don't have CORS headers set, and you try to do an XHR, so XML HTTP request to say facebook.com, then the browser will actually download facebook.com, so access the resource, but then we'll check afterwards if the same origin policy is actually fulfilled or not. So it will download the resource, it'll access the resource, but it will not allow access to the content. This obviously might be a problem if you have certain actions that can be triggered by just visiting a website. In CORS, the specification says, okay, just with a usual normal GET request, we assume that no damage can be done. But however, if, for example, we can do a request that has complex headers set, so for example, for authentication or using cookies or such, then we do a pre-flight request. That means we first, before we actually try to contact this the resource, we send an options request to the resource and say, okay, hi, is it okay if I allow it access to you or not? And then the server, so the target server, can actually say, okay, it's okay, you may access the resource. And only then the request is actually sent. Because actually, if this was not the case, there might actually be state-changing operations going on by just doing XHR, sorry. Even though maybe the access to the resource itself was denied, so the JavaScript running on attacker.org could not actually read the content, but it might trigger an action on the server side. So we need to rethink our notion of this server origin check. Is it also a problem? Might we have problems with this kind of state-changing requests as well? So, and should we actually do one pre-flight request for each and every request that also goes to same origin resources? But this is actually an open problem we're discussing right now. And yeah, that's just wanted to share this with you. Okay, so with this, I want to thank you for your attention. And I'm happy to answer any questions you might have.
Are there any questions from the audience? People getting tired. Okay, I have one question. So, did you approach some standard committee like WC3 or so to wrap this within a standard or so?
Okay, so right now we're actually in the process of getting a more in-depth view of our ideas, especially if it coming to plugins and such. I actually talked to Frederic Braun from Mozilla, who's also giving a talk tomorrow, and he also said we should actually discuss this first internally and then do a proposal to the W3C. But since this now, also our implementation only looks at browsers specifically and not plugins as such, we haven't yet approached those guys, but I think it's down the road somewhere from here.
Any more questions from the audience? Okay, if not, then please thank the speaker again.